One important graph to explain some of the nuclear processes is what we call the binding energy plot. In this case, we have a graph of binding energy per nucleon in MeV versus the nucleon number. Binding energy per nucleon. That's for each nucleon, we calculate the binding energy and divide that by A. That's binding energy per nucleon. And the nucleon number here is A. If you look at this graph, it's going to look somewhat like this. Notice that it peaks for iron 5626. That's the largest binding energy per nucleon, for iron 56 per 26. Essentially, that's the most stable nucleon. Now, if we go down to smaller nuclei, you notice we have some peaks here. These peaks correspond to stable nuclei that correspond to filled shells. But overall, you see the trend. We have low binding energy here because we don't have many neutrons. But here, since we have more neutrons than protons, so we actually have more binding energy. But what does this mean? The fact that we have a maximum here. If we start with an atom here, and if it's going to break into smaller atoms via decay, alpha decay and numerous decays as they happen, so we go from a less stable atom, nucleus, to more stable nucleus as we go this way. The difference in energy, since here we have more binding energy in that nucleus than here, so the difference in binding energy is going to be emitted. First, the process of breaking large atoms into small atoms is what we call fission, a fission reaction. Okay, that's what we have here, when we are going from large atoms to smaller atoms. And that fission reaction is going to result in an emission of heat that's due to the difference in binding energy per nucleon. From the other side, if we take some of these small nuclei and combine them to make larger atoms, like what happens in the sun. Hydrogens combine in deuterium, deuterium combine into helium, etc. Now, when that happens, first look at the difference is much bigger. So we go from very tiny binding energy per nucleon to a large one. But again, we go from low binding energy to high binding energy. The difference in energy is going to be emitted as well. But there is more difference in binding energy than through the fission process. So in fusion, we generate more energy when we have fusion than when we have fission. Let's look at a couple of examples. Which element has the highest binding energy per nucleon? We already answered that. Iron is really Fe. You notice here 26, so 2656. That's the most binding energy. Now neon, that's 10, so Z equal to 10, so that's going to be somewhere here. Iodine, Z is equal to 53, so that's going to be probably somewhere here. Which of the following is the most correct for the total binding energy for an iron atom? Okay, so it's given us several numbers for the iron atom. So we just go back to the graph and read it. 0, 2, 4, 6, 8. So this is going to be 10. The one is missing there, so it's about 9. So our answer is 9 MeVs.